In the middle of North America, far from any modern coastline, there are places where the rocks are filled with the remains of sea monsters. Kansas, South Dakota, Manitoba, Alberta. Today they are prairies, badlands, farmland, and quiet inland towns. But 80 million years ago, they lay beneath a warm inland ocean that split an entire continent in two. And within that ocean, almost everything was trying to eat something else. Giant marine lizards ruled waters that now lie beneath grass and stone. Sharks hunted alongside reptiles that grew to whale like sizes. Long necked marine reptiles gave birth in open water, where newborns entered the food web immediately. Even parts of the seafloor could become starved of oxygen, preserving the evidence of a world where survival was never guaranteed. This is not a story about a single monster. It is a story about an ecosystem, a vanished sea so productive that it supported an extraordinary concentration of predators, from giant fish and sharks to some of the largest marine reptiles that ever lived. And the most remarkable thing about this ocean was not any one creature. It was the system that made so many creatures like that possible. In today's story, we're going back into that forgotten sea. Imagine opening a map of North America and watching the familiar outlines begin to blur. Coastlines drift inward, river valleys disappear beneath advancing water, low plains sink below shallow seas. Around 80 million years ago, during the Late Cretaceous, much of the continent looked very different from the one we know today. The Cretaceous was the final period of the dinosaur age, the last chapter before the extinction that would eventually transform life on Earth. Dinosaurs still walked across broad landscapes, pterosaurs crossed the skies, and marine reptiles occupied waters stretching across large portions of the globe. Although the cast of animals often captures attention first, the shape of the world itself played an equally important role in determining which creatures could thrive. One reason was sea level. Across the planet, oceans stood far higher than they do today. Broad estimates suggest that late Cretaceous seas rose roughly 200 to 250 meters above modern sea level. As water expanded across continental margins, low lying regions that are now dry land became submerged. Areas that would one day hold farms, grasslands, towns, and forests spent millions of years beneath marine waters. North America was reshaped by this flooding. A long inland sea stretched through the continent's center, dividing the land into two major regions. To the west lay Laramidia, a narrow strip of land bordered by mountains and ocean. To the east stood Appalachia, separated from its western counterpart by a broad marine corridor. Animals living on one side could remain isolated from those on the other for immense spans of time, creating distinct ecological worlds connected only by the sea between them. That sea became known as the Western Interior Seaway. It extended for thousands of kilometers from northern regions near the Arctic to warmer southern waters connected to the ancient Gulf of Mexico. In many places, it remained relatively shallow, allowing sunlight to penetrate through much of the water column. Warm temperatures and steady exchanges between northern and southern marine environments helped create conditions favorable for an extraordinary variety of life. Nothing about this setting belonged to a fantasy world. The continents were familiar. The oceans followed recognizable physical rules. Winds moved moisture across the landscape, rivers carried sediment toward the coast, and marine organisms responded to the same ecological pressures seen in modern environments. The difference lay in climate, geography, and sea level, which combined to produce habitats that no longer exist on the continent today. Shallow seas often become centers of biological abundance. Sunlight fuels microscopic drifting organisms near the surface. Nutrients arriving from rivers and coastal systems support further growth. Small creatures feed upon that productivity. Larger animals feed upon them, and energy moves upward through increasingly complex food webs. Across the Western Interior Seaway, these relationships unfolded over immense distances, linking countless species through an interconnected marine system. As millions of years passed, the seaway became more than a flooded corridor dividing land. It evolved into one of the richest marine ecosystems of the late Cretaceous, a place where abundant life provided opportunities for hunters of every size, from swift fish to the largest predators that would come to define this remarkable ocean. A traveler crossing North America during the late Cretaceous would have encountered a journey interrupted by water. Land stretched westward, land stretched eastward, and between them lay a marine passage that occupied the heart of the continent. The Western Interior Seaway was not a narrow channel or an isolated basin. It formed a broad inland ocean that extended through the center of North America for millions of years, reshaping geography on a continental scale. Its reach connected distant environments into a single marine system. Northern waters linked toward the Arctic realm, while the southern end opened toward warmer tropical seas. Through this connection, currents carried nutrients, sediments, and living organisms across enormous distances. Fish, sharks, marine reptiles, and countless smaller creatures could move along pathways that stretched from one climate zone to another. The seaway functioned as a corridor, joining ecosystems that otherwise would have remained separated by thousands of kilometers of land. Traces of that corridor remain scattered across the continent, from Texas through the Great Plains and northward toward Montana. Layers of rock preserve evidence of a vanished sea. Fossils emerge from landscapes that now appear far removed from any coastline. Shells, teeth, vertebrae, and fragments of entire skeletons reveal the presence of animals that once swam through waters, occupying regions now covered by grasslands, ranches, farmland, and river valleys. The memory of the seaway survives within chalks, shales, limestones, and other marine sediments. Each layer records conditions that existed when mud settled to the bottom, when shells accumulated across the seafloor, or when microscopic organisms completed their life cycles and became part of the growing sediment below. These rocks are more than stone, they are pages assembled gradually through time, preserving details of environments that vanished tens of millions of years ago. Among the most celebrated of these records is the Niobrara chalk, formed largely from the remains of microscopic marine organisms. It preserves fossils with extraordinary detail. Bones, teeth, and delicate skeletal structures can remain recognizable because fine sediments buried them before waves. Scavengers and decay erase their traces. In some cases, paleontologists recover specimens that reveal interactions, injuries, and anatomical features that would otherwise have disappeared from the fossil record entirely. Although maps often portray the Western Interior Seaway as a single continuous body of water, its boundaries never remained fixed. Water advanced across portions of the continent during some intervals and retreated during others. Shorelines migrated. Coastal habitats expanded, contracted, and shifted location. River systems altered the shape of local environments, while changing sea levels transformed connections between regions. The geography experienced by marine animals during one period could differ substantially from conditions a few million years later. Life responded to those changes. Prey populations followed favorable habitats. Migratory routes adjusted as coastlines moved. Areas rich in food attracted hunters, and hunters carried ecological pressure wherever they traveled. The pathways linking northern and southern waters remained active, though their shape and extent changed through time. Seen across millions of years, the Western Interior Seaway becomes more than a stretch of water dividing a continent. Its shorelines drifted, its habitats shifted, and its living communities rearranged themselves again and again, turning the ocean into a changing stage, where every movement of the sea reshaped the lives within it. Every enormous hunter begins with something almost invisible, far above the seafloor, where sunlight filtered through warm water. Countless tiny organisms drifted through the Western Interior Seaway. Their presence rarely appears in museum displays, and their fossils seldom command attention the way giant skeletons do. Even so, they formed the living foundation upon which the entire marine world depended. These organisms were plankton, tiny drifting life forms carried by currents rather than traveling under their own power. Some captured energy from sunlight, transforming it into organic matter that could support other creatures. Across the broad waters of the seaway, trillions upon trillions of these microscopic producers turned light into food, creating a constant flow of energy through the ecosystem. Small animals fed upon this abundance. Tiny crustaceans filtered plankton from the water. Larval forms of many marine creatures spent portions of their lives feeding within these drifting communities. Schools of fish gathered where productivity was highest, consuming the small organisms concentrated by currents and seasonal changes. Life accumulated layer upon layer, each level supported by the one below it. As fish populations expanded, opportunities appeared for larger predators. Medium sized hunters fed on smaller fish, growing in number wherever food remained plentiful. Energy moved upward through the ecosystem in a continuous exchange of feeding, growth, reproduction, and survival. What began as microscopic life near the surface eventually became flesh, bone, shell, and muscle distributed across an immense marine landscape. Among the most common inhabitants of that landscape were ammonites, shelled cephalopods related to the broader group that includes modern squid, octopuses, cuttlefish, and nautiluses. Their coiled shells appeared in astonishing numbers throughout Cretaceous seas. Some drifted through open water, while others occupied different ecological roles depending on species and habitat. Their abundance made them an important source of food for many larger animals. The richness of the seaway extended far beyond fish and ammonites. Fossil deposits preserve evidence of bivalves resting within sediments, marine snails moving across the seafloor, and echinoderms inhabiting a variety of underwater environments. Each group contributed to the circulation of energy through the ecosystem. Some filtered food from the water, others grazed, scavenged, or preyed upon smaller organisms. Together, they formed an intricate web of interactions stretching from shoreline environments to deeper offshore waters. When prey becomes abundant across many levels of an ecosystem, predators often flourish alongside it. A sea crowded with fish can support larger fish. Large fish can sustain sharks. Sharks, in turn, occupy feeding relationships alongside marine reptiles and other hunters. Ecological opportunity expands upward through the food web, allowing multiple predatory lineages to coexist within the same environment. This helps explain a defining characteristic of the Western Interior Seaway. Its reputation for danger emerged from productivity. The waters generated enough biological wealth to sustain numerous hunters at the same time. Powerful jaws, sharp teeth, crushing bites, and swift pursuit all depended on a foundation built from drifting life scarcely visible to the human eye. From that foundation arose some of the most successful marine predators of the late Cretaceous, creatures whose ancestry began on land before adapting so completely to ocean life that they came to dominate much of the seaway. Among the many predators moving through the Western Interior Seaway One group carried an evolutionary story written across two very different worlds. Their distant ancestors belonged on land, walking on solid ground as members of the squamate lineage, the same broad group that today includes lizards and snakes. By the late Cretaceous, however, some of those descendants had become masters of marine life, spending their lives far from any shoreline. These animals were mosasaurs, marine lizards that are often mistaken for dinosaurs. Despite sharing the same age as many famous dinosaurs, they belong to a different branch of the reptile family tree. Their closest living relatives remain a subject of scientific discussion, though their connection to squamates is well established. Fossils preserve a body plan shaped by life in water, one that differs dramatically from the terrestrial forms from which they evolved. A mature mosasaur possessed a long, streamlined body designed for movement through open seas. Paddle like limbs replaced weight bearing legs. Large jaws lined with sharp teeth occupied the front of an elongated skull. Behind them stretched a muscular torso, ending in a powerful tail capable of generating thrust with every sweep through the water. Taken together, these features created predators well suited to pursuing prey across a range of marine environments. The fossil record places mosasaurs entirely within the late Cretaceous. They appeared comparatively late in the age of reptiles and diversified rapidly during the final chapter of that era. Across roughly 25 million years, they expanded into numerous ecological roles and spread through oceans around the world. Within the Western Interior Seaway, they became some of the most successful large predators known from the region. Their rise did not begin with giants. Early mosasaurs were generally smaller animals inhabiting coastal environments. They hunted near shorelines and occupied habitats where land and sea remained closely connected. Through evolutionary time, many lineages moved farther into marine settings. Adaptations accumulated generation after generation, gradually producing animals increasingly specialized for permanent life in open water. The mechanics of their swimming reflected their ancestry. Unlike fish, which often generate movement through different body motions, mosasaurs propelled themselves using side to side undulations. Waves of muscular motion traveled through the body and into the tail, pushing water backward and driving the animal forward. This pattern retained echoes of a terrestrial past while functioning effectively in marine environments. Evidence from fossils suggests that later mosasaurs refined this system further. Tail anatomy changed through time, with advanced species developing structures that improved swimming efficiency. Vertebrae near the tail became modified in ways that supported stronger propulsion, while the tail itself evolved toward shapes better suited for sustained movement through open seas. These changes help transform capable swimmers into highly effective marine hunters. Their story reveals how evolution can reshape an animal across millions of years. Creatures descended from land dwelling reptiles gradually acquired the anatomy needed to thrive in environments their ancestors could never have occupied. By the height of their success, mosasaurs ranged through major oceans and dominated many marine ecosystems. Within that diverse group, some species grew far larger than others. Their skulls lengthened, their bodies expanded, and their influence spread across the food web, producing forms that stood among the most formidable predators the Western Interior Seaway would ever contain. Few animals embodied the power of the Western Interior Seaway more completely than Tylosaurus. Among the many mosasaurs that inhabited late Cretaceous oceans, this predator has become one of the best known, partly because of its impressive size and partly because its fossils offer unusually detailed glimpses into life at the top of the food web. When paleontologists reconstruct the seaway's largest hunters, Tylosaurus often occupies a central place in that picture. Its proportions were striking. A long body stretched behind a massive skull built for seizing and subduing prey. Strong jaws carried rows of sharp teeth, while a muscular tail supplied the thrust needed to move efficiently through open water. Some mosasaurs reached lengths approaching 50 feet, roughly comparable to the length of a modern bus. Such dimensions placed them among the largest marine reptiles of their time and gave them access to prey unavailable to smaller hunters. The name Tylosaurus is often interpreted as knob lizard, a reference to the unusual structure at the front of its snout. Fossils reveal a blunt, reinforced extension of the skull, unlike the pointed rostrums seen in many other marine predators. Researchers continue to explore the exact function of this feature, though its robust construction suggests it may have played a role in feeding, combat, or interactions with other animals. Whatever its purpose, it gave Tylosaurus a distinctive appearance within a sea already crowded with unusual forms. Understanding the lifestyle of such an animal requires piecing together many different kinds of evidence. Paleontologists study tooth shape to estimate feeding habits. Jaw structure provides clues about bite force and prey handling. Stomach contents occasionally preserve direct records of what an animal consumed. Bite marks found on bones reveal interactions that occurred during life or after death. Each source contributes a fragment of information, allowing scientists to build a picture grounded in physical evidence rather than speculation alone. Those clues consistently point toward a predator occupying one of the highest positions in the ecosystem. Tylosaurus likely hunted a wide range of animals available within its environment. Fish formed part of that menu. Seabirds moving across marine habitats could become prey. Smaller marine reptiles were vulnerable under the right circumstances. Turtles and other animals inhabiting the seaway may also have been targeted when opportunities arose. A hunter of this size benefited from flexibility, taking advantage of whatever resources the ecosystem provided. Even an apex predator, however, existed within biological limits. Large body size reduced some dangers while introducing others. Injuries could accumulate through hunting accidents or conflicts with rivals. Disease affected prehistoric animals just as it affects modern ones. A carcass that escaped predation during life could still become food for scavengers afterward. Young individuals faced challenges far different from those encountered by fully grown adults and remained exposed to threats that disappeared only as they matured. Seen through the fossil record, Tylosaurus emerges as a formidable hunter shaped by the opportunities of a productive sea. Its success depended upon the same ecological network supporting every other creature around it. The largest mosasaurs occupied the highest levels of that system, yet they remained participants within it, surrounded by competition, risk, injury, and death, like every other inhabitant of the Western Interior Seaway. Some of the most revealing fossils from the Western Interior Seaway carry signs of damage long after the animals themselves disappeared. Bones bear punctures, healed fractures, cross ribs and vertebrae. In certain specimens, paddles appear broken, distorted, or partially destroyed. These traces provide rare glimpses into moments of conflict that unfolded millions of years ago and suggest that danger did not always arrive from a different species. Among the most intriguing discoveries are mosasaur remains marked by bites that appear to have come from other mosasaurs. Fossils examined from seaway deposits preserve evidence of powerful jaws meeting bone with enough force to leave lasting scars. In some cases, the injuries healed during life, indicating that the animal survived the encounter. Other specimens show damage without clear signs of recovery, leaving open the possibility that the attack occurred near the end of the animal's life or after death. The challenge for paleontologists is determining exactly what happened. A bite mark records contact, not motive. Several explanations can fit the same evidence. Two predators might have competed for food. Individuals could have clashed during reproductive interactions. Territorial disputes may have occurred in certain circumstances. A carcass floating or resting on the seafloor could attract scavengers. Each possibility remains scientifically plausible, depending on the details preserved in the fossil. Because of these uncertainties, researchers draw careful boundaries around their conclusions. A damaged bone can demonstrate that a bite occurred. It may reveal the direction of force or the size of the teeth involved. Beyond that point, certainty becomes more difficult. The fossil record preserves outcomes far more often than it preserves behavior. Scientists must therefore balance interpretation with restraint, allowing evidence to guide the story without extending beyond what the remains can support. Sometimes the shape of the wound offers additional clues. Different predators possess different tooth structures, and those structures can leave distinctive marks. Long, conical teeth create patterns unlike those produced by broad cutting teeth. Measurements of spacing between punctures may correspond to known jaw sizes. Through comparisons with other fossils, paleontologists can occasionally identify the most likely source of an injury, though complete certainty remains uncommon. For young mosasaurs, the seaway presented even greater challenges. Adults occupied some of the highest positions in the food web, but juveniles lacked the size and strength that offered protection later in life. Their smaller bodies made them vulnerable to a wider range of predators. Large sharks patrolled the same waters. Giant predatory fish pursued opportunities wherever prey could be found. A young mosasaur entering this environment faced hazards from multiple directions long before reaching maturity. Evidence suggesting cannibalism or predation among closely related species adds another layer to this picture. Food webs are often imagined as orderly ladders, with large hunters feeding on smaller animals below them. The seaway appears more complicated. Predators sometimes became prey. Competition could emerge among animals occupying similar ecological roles. The boundaries separating hunter and hunted shifted depending on age, circumstance, and opportunity. Seen through this lens, even the largest mosasaurs remained participants in a system where risk flowed throughout the food web. Their power granted advantages, though it offered no exemption from injury, conflict, or death. Across the same waters traveled another formidable predator, one built not as a reptile, but as a giant fish. Not every dominant hunter in the Western Interior Seaway belonged to the reptiles. Moving through the same waters was a giant bony fish called Xiphactinus, an animal whose appearance combined speed, size, and a mouth filled with formidable teeth. Although comparisons are imperfect, paleontologists sometimes describe it as resembling an enormous tarpon armed with fangs, provided one remembers that it was not related to modern tarpons and occupied a very different place in evolutionary history. Its body was built for pursuit. Long and streamlined, Xiphactinus possessed proportions suited to active hunting in open water. Large jaws extended forward from a narrow head, creating a weapon lined with sharp teeth capable of gripping struggling prey. Every aspect of its anatomy suggests an animal adapted for rapid movement and sudden attacks. Where smaller fish relied on concealment or maneuverability, Xiphactinus appears to have relied on speed and overwhelming force. Fossil evidence indicates impressive size. Many large individuals are estimated to have measured between roughly 4.5 and 6 meters in length. Such dimensions place them among the most significant predatory fish in the seaway ecosystem. They occupied waters already crowded with marine reptiles and sharks, demonstrating that the abundance of available prey could support multiple large hunters at the same time. Among all known Gifactinus discoveries, one specimen has become particularly famous. Displayed at the Sternberg Museum, it preserves a remarkable scene frozen in stone. Inside the larger fish rests another fish called Gillicus. The smaller animal remains preserved within the body cavity of its predator, creating what is often described as a fish within a fish fossil. This specimen carries unusual scientific value because it records an actual feeding event. Many aspects of prehistoric life must be reconstructed from indirect evidence. Tooth shape suggests feeding habits. Jaw anatomy implies possible prey preferences. Bite marks hint at interactions between animals. The Sternberg specimen preserves something far more direct. It shows one animal consumed by another, eliminating much of the uncertainty that normally surrounds dietary interpretations. The condition of the fossil reveals an additional detail. The Gillicus shows little sign of digestion. Its skeleton remained largely intact within the body of the predator. Because of this, researchers have suggested that Ziphichtinus likely died not long after swallowing its meal. The exact cause remains uncertain. Some have proposed internal injury, while others point to complications associated with swallowing exceptionally large prey. Whatever the mechanism, the fossil captures a moment in which successful hunting may have contributed to the predator's own demise. That possibility adds another dimension to understanding the seaway. Feeding represented opportunity, yet it also carried risk. Large prey could struggle, bones could cause injury. Energetic demands pushed predators toward decisions with consequences that were not always favorable. The fossilized Ziphichtinus and its final meal preserve evidence of those realities more clearly than almost any written description ever could. Viewed within the broader ecosystem, Xiphactinus occupied an important position between smaller prey species and the largest marine hunters. It was a predator capable of consuming substantial animals, while remaining part of a food web that included even larger competitors and threats. In the Western Interior Seaway, power existed on many levels, and Xiphactinus formed one link in a hierarchy that extended far beyond any single hunter. Scattered through marine sediments of the Western Interior Seaway are teeth shaped like polished blades. They often survive when softer parts of the animal have vanished, leaving behind durable clues to one of the most important sharks of the Late Cretaceous. Those teeth belong to Cretoxyrhina mantelli, a predator that moved through the same waters as giant fish, marine reptiles, diving birds, and flying pterosaurs. Among paleontology enthusiasts, Cretoxyrhina is sometimes called the Ginsu shark, a nickname inspired by the sharp cutting edges of its teeth. The comparison captures something important about its feeding adaptations. These were not crushing teeth designed for armored prey. They were slicing tools capable of cutting through flesh with efficiency. Their form reflects an animal specialized for pursuing and consuming large active prey in open marine environments. Fossils of Cretoxyrhina occur throughout deposits associated with the Western Interior Seaway, revealing a broad geographic distribution. Its remains appear in regions that once formed part of the continent-spanning marine system, placing the shark among the recurring predators of this ecosystem. Wherever productive waters supported large prey populations, Cretoxorhina found opportunities to thrive. It occupied the role of a large pelagic predator. Pelagic refers to animals that live in open water rather than on the seafloor. Instead of remaining tied to reefs, coastal shallows, or bottom habitats, pelagic hunters move through the water column itself. Such a lifestyle favors efficient swimming, strong sensory abilities, and the capacity to cover considerable distances while searching for food. Cretoxorhina possessed many of the features expected from an animal adapted to that way of life. The fossil record provides evidence that its interactions extended across multiple parts of the seaway ecosystem. Research has linked Cretoxorhina to feeding relationships involving other marine animals, including pterosaurs. In certain cases, fossil remains preserve traces suggesting contact between shark teeth and the bones of flying reptiles associated with coastal and marine environments. These discoveries offer reminders that ecological connections did not stop at the water's surface. Animals feeding above the sea could still become part of marine food webs under the right circumstances. Within the open waters, Cretoxorhina shared space with mosasaurs and other large predators. It is tempting to imagine a simple hierarchy in which one always dominated the other, yet ecosystems rarely operate according to such straightforward rules. Encounters between predators depend on many factors. Size matters, age matters, location matters. A juvenile mosasaur faced different risks than a mature adult. A shark hunting in one habitat might experience opportunities unavailable elsewhere. Prey availability could alter behavior from region to region and from season to season. This complexity broadens the picture of the Western Interior Seaway. The danger present within the ecosystem did not originate from a single dominant species. Multiple predator lineages occupied overlapping roles, each shaped by different anatomical solutions to the same challenge of finding food. Marine reptiles, giant fish, and sharks all participated in the same network of competition and opportunity. Cretoxorhina illustrates one approach: a fast-moving hunter armed with cutting teeth and adapted for life in open water. The Seaway, however, also supported sharks that followed a very different path, replacing slicing blades with crushing dental batteries designed for prey protected by shells and armor. A collection of fossil teeth can sometimes reveal an animal's lifestyle more clearly than an entire skeleton. Among the sharks of the Western Interior Seaway, few examples illustrate this better than Tychodus. At first glance, its teeth appear unusual when compared with the sharp cutting edges associated with many famous predators. They seem broad, flattened, and almost cobblestone-like, as though they belonged to an animal feeding on something very different from swift fish or large marine reptiles. Tychodus was a large Cretaceous shark specialized for durophagy, a feeding strategy based on consuming hard-shelled prey. Instead of slicing flesh, it relied on crushing strength. Its mouth contained rows of flat teeth arranged like a pavement, creating a durable grinding surface capable of breaking apart resistant shells. Fossils show these teeth occurring in great numbers, providing abundant evidence of how this shark interacted with its environment. The contrast with predators such as Cretoxorhina is striking. One carried blade-like teeth designed for cutting through soft tissue. The other evolved dental equipment built to withstand repeated impacts against armor. Both occupied the same broad marine ecosystem, yet each followed a different evolutionary path. Their coexistence demonstrates how multiple large predators could thrive by targeting different food resources rather than competing for exactly the same prey. The seaway offered many opportunities for a shell crusher. Large clams inhabited marine sediments. Other bivalves filtered food from surrounding waters. Various hard-bodied organisms occupied habitats ranging from coastal environments to deeper settings. For an animal capable of cracking protective coverings, these creatures represented concentrated sources of nutrition that remained inaccessible to many other predators. Evidence suggests that some Tychoda species reached considerable size. Although precise estimates remain challenging, fossil interpretations and research have placed certain species within the size range occupied by very large modern sharks. Such dimensions make an important point about the ecology of the seaway. Gigantism was not restricted to hunters pursuing large prey through open water. An animal could grow to impressive proportions while feeding primarily on armored organisms gathered from productive marine habitats. This diversity of feeding strategies helps explain how the ecosystem supported so many predators simultaneously. A shark adapted for shell crushing occupied a different ecological niche from one specializing in fish or marine reptiles. Energy moved through separate pathways before eventually reaching different hunters. The richness of the food web created room for specialization, allowing multiple lineages to flourish side by side without relying on identical resources. Looking across the seaway as a whole reveals a layered landscape of danger. Some predators attacked with cutting teeth designed to slice through flesh. Others swallowed prey whole when size and opportunity allowed. Tychotus introduced another form of threat, one based on crushing power rather than speed or sharpness. Hard shells that protected smaller animals from many predators offered less security when confronted by jaws built specifically to overcome them. The ecosystem becomes more complex with each new participant. No single hunting strategy defined life within these waters. Different predators solved different challenges, creating a marine community shaped by evolutionary experimentation across millions of years. Sharks occupied several of those roles, though they shared the seaway with another distinctive group of marine reptiles, animals whose movement through the water relied on four powerful flippers and whose history stretched back long before mosasaurs entered the scene. Long before mosasaurs spread through the world's oceans, another lineage of marine reptiles had already established itself in the water. Their history stretched back tens of millions of years, crossing multiple geological periods and surviving major environmental changes. By the time the Western Interior Seaway flourished during the Late Cretaceous, these animals remained an important part of the marine ecosystem. They were the plesiosaurs, a group whose appearance differed from almost every other large reptile sharing their world. Plesiosaurs were marine reptiles equipped with four powerful flippers. They were neither dinosaurs nor mosasaurs, belonging instead to their own distinct evolutionary branch. Fossils reveal bodies shaped for life at sea, with limbs transformed into broad paddles and skeletons adapted for continuous swimming. Their persistence across such immense spans of time reflects a design that proved successful in many different marine environments. Two broad body plans appeared within the group. Some species carried long necks supporting relatively small heads. Others possessed shorter necks combined with larger skulls and more robust jaws. These contrasting forms likely occupied somewhat different ecological roles, allowing multiple kinds of plesiosaurs to coexist across marine habitats. The variation demonstrates that plesiosaurs were not a single uniform type of animal, but a diverse collection of species shaped by different evolutionary pressures. Their movement through the water also differed from that of mosasaurs. Earlier sections introduced the side-to-side propulsion generated by a mosasaur's body and tail. Plesiosaurs followed another approach. Their four flippers worked together in a coordinated swimming motion, often compared to underwater flight. Instead of relying primarily on a sweeping tail, they generated thrust through the repeated movement of all four limbs. This created a style of locomotion unlike that of sharks, mosasaurs, or most modern marine vertebrates. The longevity of the group is particularly striking. Plesiosaurs occupied marine ecosystems long before mosasaurs emerged as major predators and continued living alongside them after those newer arrivals diversified. Within the Western Interior Seaway, they remained familiar members of the community, moving through waters already crowded with fish, sharks, turtles, ammonites, and marine reptiles of many kinds. The long-necked forms have inspired considerable scientific discussion. Researchers have proposed several possibilities regarding how such necks may have been used while hunting. A flexible neck might have allowed certain species to approach prey from unexpected angles or position the head independently from the larger body. Debate continues because soft tissues and behavior rarely fossilize, leaving room for multiple interpretations. Even so, the distinctive anatomy suggests feeding strategies different from those employed by predators, relying on speed, crushing force, or massive jaws. Their lives involved more than movement and feeding. Fossil evidence from a species called Polycotylos has provided strong support for live birth in at least some plesiosaurs. One remarkable specimen preserved an unborn young animal within the body cavity of its mother. This discovery indicates that certain plesiosaurs gave birth at sea rather than returning to land. That evidence broadens the picture of the Western Interior Seaway. The ecosystem supported hunting and predation, yet it also contained courtship, reproduction, growth, and family beginnings. New life entered the world within the same waters occupied by large predators, making reproduction itself part of the ongoing rhythm of survival that shaped every corner of the seaway. Far from any shoreline, a marine reptile drifted through the waters of the Western Interior Seaway, carrying new life within its body. When the time came, the young would enter the world directly into the ocean. There would be no journey to a nesting beach, no buried clutch of eggs waiting in coastal sand. Birth itself occurred within the same marine realm that sustained predators, prey, and countless other forms of life. For highly adapted marine reptiles, returning to land may have been difficult or impossible. Millions of years of evolution had transformed bodies, once suited for terrestrial movement, into forms specialized for swimming. Limbs became flippers, skeletons changed shape, entire life cycles grew increasingly tied to the sea. For some species, reproduction appears to have followed that trend, freeing them from dependence on land-based nesting sites. Live birth represented one solution to this challenge. Instead of depositing eggs in a terrestrial environment, the developing young remained within the mother's body until birth. Fossil evidence from certain marine reptiles supports this strategy, demonstrating that at least some species completed the earliest stages of life entirely within the ocean. The adaptation allowed animals to remain in marine habitats throughout the year without the need to return to shore. Modern whales provide a useful comparison, though not a close evolutionary relationship. Whales are mammals, while marine reptiles belong to very different branches of the vertebrate family tree. Even so, both groups illustrate how life in water can encourage similar solutions to practical problems. Certain modern reptiles also give birth to live young. These examples show how evolution can arrive at comparable outcomes through separate histories when organisms face similar environmental demands. Birth, however, marked only the beginning of a far greater challenge. Newborn marine reptiles entered an ecosystem already occupied by large predators. Their smaller size made them easier targets. Limited swimming ability reduced escape options. Experience had yet to be gained. Every skill required for survival remained in its earliest stages of development. The ocean offered opportunity, though it demanded immediate adaptation from even its youngest inhabitants. These pressures likely influenced where young animals spent their earliest periods of life. Some researchers have suggested the possibility of nursery like areas within marine ecosystems, locations where environmental conditions may have provided certain advantages for juveniles. Shallow regions can offer abundant food and, in some circumstances, reduced exposure to particular predators. Evidence for specific nursery grounds in the Western Interior Seaway remains limited, so such ideas must be considered carefully. Even so, the concept reflects broader ecological patterns observed in marine environments. Questions surrounding parental behavior are even more difficult to answer. Fossils occasionally preserve evidence of reproduction, growth, or developmental stages, yet detailed parenting activities rarely leave direct traces. Whether marine reptiles cared extensively for their young after birth remains uncertain. The fossil record offers only fragments, leaving much of that story beyond our reach. Even with those uncertainties, one fact remains clear. Life began within waters already occupied by sharks, giant fish, marine reptiles, and other hunters. Growth unfolded alongside risk from the very first moments. The Western Interior Seaway contained feeding, migration, courtship, and birth as interconnected parts of a single ecosystem. Above those waters, another community moved through the air, following coastlines, searching for food, and linking the marine world to the skies overhead. A shadow passing across the surface of the Western Interior Seaway did not always belong to a cloud. At times, it came from a flying reptile riding air currents above the water, scanning the marine world from a very different perspective. Among the most recognizable of these aerial animals was Pteranodon, a creature whose fossils have become closely associated with the late Cretaceous landscapes bordering the Great Inland Sea. Pteranodon was neither a dinosaur nor a bird. It belonged to the pterosaurs, a separate group of flying reptiles that evolved powered flight long before birds achieved their modern diversity. Its anatomy reflected a life spent largely in the air. Long wings stretched outward from an elongated fourth finger, creating an impressive wingspan. A toothless beak projected from the skull, while a prominent crest extended from the back of the head. The exact purpose of that crest remains debated, though researchers have proposed roles involving display, species recognition, or aerodynamic effects. The geography of the Western Interior Seaway provided favorable conditions for animals adapted to soaring flight. Coastal margins, marine corridors, and productive waters supported abundant food resources. Fossil discoveries show that Pteranodon lived around this seaway and formed part of the broader ecosystem connecting land, air, and water. Though capable of long-distance travel, its existence remained closely tied to the marine environment below. Evidence suggests that feeding played a major role in that connection. The shape of the beak and the distribution of fossils indicate a lifestyle associated with marine food sources. Researchers have proposed that Pteranodon likely captured fish and other prey from the water or near its surface. Exact hunting techniques remain uncertain, yet the broader relationship appears clear. The flying reptiles depended on resources generated by the same productive ecosystem that sustained sharks, giant fish, turtles, ammonites, and marine reptiles. This relationship placed pterosaurs within the food web rather than above it. Animals feeding over the sea remained vulnerable to hazards originating from the sea itself. Fossil evidence has linked Pteranodon to interactions involving Cretoxorina, the large pelagic shark discussed earlier. Certain remains preserve signs consistent with contact between shark and pterosaur, offering rare evidence that these very different animals occasionally intersected within the ecosystem. The significance of such discoveries extends beyond any individual encounter. They demonstrate that ecological boundaries were more permeable than they may first appear. Air and water did not function as isolated worlds. Energy, nutrients, and risk moved between them. An injured animal floating at the surface could attract marine scavengers. A carcass drifting through coastal waters might become part of the underwater food web. Low-flying feeding behavior could occasionally bring aerial hunters within reach of predators below. The fossil record cannot reconstruct every detail of those events. It does not preserve complete scenes or continuous narratives. What it provides are fragments, clues that reveal connections among organisms sharing the same environment. Those fragments suggest a seaway where interactions extended upward into the air as well as downward into the water column. Pteranodon occupied that aerial layer, linking sky and sea through its daily search for food. Yet, even as flying reptiles crossed above the waves, another group of animals pursued a different path. These creatures entered the water directly, diving beneath the surface and becoming active participants in the marine world itself. Not all birds of the late Cretaceous remained above the water. Some entered the sea directly, pursuing prey beneath the surface and developing bodies suited to an aquatic way of life. Among the most remarkable examples was Hesperornis, a member of a group known as the Hesperornithiforms. These birds occupied a place in evolutionary history that feels both familiar and unfamiliar at the same time, combining recognizable avian features with traits rarely associated with birds today. Hesperornis and its relatives belonged to some of the earliest known birds fully adapted to marine living. Fossil evidence shows that Hesperornithiform birds had moved far beyond the lifestyle of small feathered animals inhabiting forests or shorelines. Their bodies reflected prolonged adaptation to water, demonstrating that birds had already begun exploring specialized ecological roles while dinosaurs still dominated terrestrial environments. One of the most noticeable changes involved their wings. Unlike modern seabirds that depend on flight to travel between feeding grounds, Hesperornis possessed greatly reduced wings that were no longer useful for powered flight. At the same time, its hind limbs became exceptionally well developed. Powerful swimming legs extended behind the body, providing propulsion during underwater pursuits. The overall appearance resembled a diving specialist far more than a bird soaring through open skies. Another feature would seem striking to modern observers. Hesperornis possessed teeth. Modern birds lack teeth entirely, using beaks to gather, tear, or manipulate food. During the Cretaceous, however, several early bird groups still retained toothed jaws inherited from distant ancestors. Fossils of Hesperornis preserve rows of teeth well suited for gripping slippery prey, providing another reminder that the evolution of birds was still unfolding during this period. Its anatomy suggests a lifestyle centered on underwater hunting. Rather than feeding primarily at the surface, Hesperornis likely pursued fish beneath the waves. Strong legs generated thrust, while the streamlined body moved through the water. Teeth helped secure prey once captured. Although exact behavior cannot be observed directly, the skeletal evidence points toward an active diver capable of exploiting food resources unavailable to many other birds. These animals shared their environment with some of the most formidable creatures discussed so far. Mosasaurs patrolled portions of the seaway. Plesiosaurs continued their long marine history. Sharks crossed open waters. Giant predatory fish searched for opportunities. Within this community, Hesperornis occupied a very different niche, yet it remained connected to the same ecological network. Their importance extends beyond the ecosystem itself. Hesperornis and related species reveal how diverse birds had already become by the late Cretaceous. Evolution was not producing a single bird design. Multiple forms emerged simultaneously, adapting to forests, shorelines, inland habitats, and marine environments. The existence of highly specialized diving birds demonstrates that major avian experimentation was already underway millions of years before the end of the Cretaceous. Life in the water carried costs alongside opportunities. A diving bird entering the sea became part of the food web rather than merely observing it from above. The same waters that supplied fish also contained predators capable of exploiting weakness, injury, or bad fortune. Survival depended on navigating those risks while competing for resources. Beneath the paths of diving birds stretched a dense layer of smaller prey, countless animals whose lives formed the foundation, supporting every hunter that moved through the Western Interior Seaway. Scattered through the rocks left behind by the Western Interior Seaway are countless spirals, preserved in chalk, shale, and limestone long after their makers disappeared. Some are small enough to fit in a hand. Others reached impressive sizes. These fossils belonged to ammonites, one of the most successful groups of marine animals in Earth's history and among the most recognizable inhabitants of Cretaceous oceans. Ammonites were extinct, shelled cephalopods. A cephalopod is a member of the group that includes squid, octopuses, cuttlefish, and nautiluses. Although ammonites shared ancestry with these animals, they developed their own distinctive appearance. Their bodies occupied coiled external shells divided into a series of chambers. As the animal grew, it built new chambers while sealing older ones behind it, creating the familiar spiral pattern found in fossils today. Those chambers served practical functions during life. By adjusting gases and fluids within them, ammonites could influence buoyancy and maintain position in the water. The shell functioned as more than protection. It formed part of a sophisticated system that helped the animal navigate its marine environment. Across millions of years, evolution produced an extraordinary variety of shell shapes, ornamentation, and sizes, making ammonites one of the most diverse marine groups of the Mesozoic era. Their abundance is reflected in the fossil record. Cretaceous marine rocks frequently contain ammonite remains in large numbers. Entire layers may preserve shells representing generations of animals that once drifted, swam, fed, and reproduced within the seaway. This abundance provides valuable information for paleontologists studying both ecosystems and geological history. Ammonites mattered in several different ways. They served as prey for larger animals. They acted as predators themselves, feeding on smaller organisms within the marine food web. They also function as index fossils. An index fossil is a fossil especially useful for dating rock layers. Because many ammonite species evolved rapidly and occupied broad geographic ranges, particular species can help identify the age of sediments in which they occur. Through ammonites, paleontologists can read time almost as though turning pages in a book. A certain species appearing within one layer may indicate a specific interval of geological history. Another species found higher in the sequence marks a different chapter. Across the Western Interior Seaway, ammonites help scientists track environmental changes, shifting habitats, and the passage of millions of years with remarkable precision. Their shells also preserve evidence of ecological interactions. Some fossils display repaired damage where the animal survived an attack and continued growing. Others show fractures, punctures, or irregular patterns suggesting encounters with predators. Determining the exact source of every injury is often impossible, yet the traces reveal that ammonites participated fully in the risks and pressures of marine life. A rich population of ammonites contributed significantly to the productivity of the seaway. Large numbers of mid-level prey animals create opportunities for larger hunters, transferring energy upward through the food web. Fish, marine reptiles, and other predators benefited from ecosystems capable of supporting abundant cephalopod populations. The success of top predators depended in part upon the success of animals much smaller than themselves. There is a striking contrast in this arrangement. Delicate spirals drifted through waters occupied by sharks, giant fish, and marine reptiles. Fragile shells existed alongside powerful jaws and enormous bodies. Together, they formed parts of the same interconnected system, one that also included another important group of marine reptiles, armored swimmers, whose protective shells offered a different strategy for survival. Amid the sharks, giant fish, flying reptiles, marine lizards, and diving birds of the Western Interior Seaway lived another group of animals whose lineage continues into the modern world. Sea turtles moved through these waters as they do in oceans today, carrying a body plan already shaped by millions of years of adaptation. Their presence adds an important dimension to the ecosystem, reminding us that the seaway supported more than dramatic predators and spectacular fossils. Late Cretaceous sea turtles formed a significant part of marine communities across the seaway. Although they did not occupy the same apex predatory role held by large mosasaurs, they were nevertheless successful marine reptiles capable of thriving in a variety of habitats. Fossil discoveries reveal animals ranging from moderate sizes to truly impressive dimensions, demonstrating that turtles had already become established members of marine ecosystems long before the end of the Cretaceous. Their most recognizable feature was the shell. Built from modified ribs and other skeletal elements, the shell provided a remarkable form of protection. For many animals, it created an effective barrier against smaller predators and environmental hazards. The shell transformed the turtle into a living fortress, allowing survival strategies unavailable to less protected creatures sharing the same waters. Protection, however, had limits. Armor reduces risk. It does not eliminate it. Large predators possessed ways of overcoming defenses that smaller hunters could not breach. Powerful jaws might target exposed limbs, the neck, or softer tissues around the edges of the shell. A sufficiently large attacker did not necessarily need to break the shell completely in order to inflict serious injury. As in every other part of the ecosystem, survival depended on a balance between defensive adaptations and the capabilities of potential predators. Young turtles faced even greater challenges. Hatchlings and juveniles lacked the size and durability of adults. Their shells remained less robust, their swimming abilities less developed, and their vulnerability much higher. The earliest stages of life likely carried significant mortality, a pattern familiar in many marine organisms both past and present. Reaching adulthood represented the successful navigation of numerous ecological hazards. Sea turtles contributed to the food web in ways extending beyond predator-prey relationships. They fed according to the resources available within their habitats, consuming different foods depending on species, age, and environmental conditions. They traveled across marine regions, connecting habitats through movement. Reproduction followed biological rhythms shaped by their evolutionary history. After death, their remains became resources for scavengers and decomposers, returning energy to the ecosystem through other pathways. Their fossils also provide valuable information for paleontologists studying the seaway. Turtle remains occur in marine deposits across multiple regions, helping researchers reconstruct habitat diversity and environmental conditions. Different species can indicate differences in ecology, geography, and water characteristics. Each fossil contributes another piece to the larger picture of how life was distributed across this enormous inland sea. Viewed together, these patterns reveal an ecosystem far richer than a simple collection of predators. Turtles, birds, ammonites, fish, sharks, and reptiles occupied interconnected roles shaped by feeding, migration, growth, reproduction, and death. The Western Interior Seaway contained conflict and competition, yet it also contained countless ordinary biological processes unfolding simultaneously. It was never a single battlefield. It was a living mosaic, composed of many overlapping lives moving through the same waters. Far below the movements of turtles, fish, birds, and marine reptiles, another world existed along portions of the Western Interior Seaway. It was a realm shaped less by teeth and speed than by chemistry. While life flourished near the surface, conditions on parts of the seafloor sometimes followed a very different pattern, creating environments that could challenge many organisms attempting to live there. Scientists use the term anoxic to describe environments containing little or no oxygen. In parts of the Western Interior Seaway, bottom waters periodically entered such states. These conditions did not cover the entire seaway at all times, nor did they transform every seafloor habitat into a biological desert. Instead, oxygen levels varied across locations and through time, creating a patchwork of environments that shifted as water, circulation, climate, and biological productivity changed. For animals living on or within the sediment, oxygen availability could determine whether a habitat remained suitable. Many bottom-dwelling creatures depend upon dissolved oxygen in the surrounding water, just as land animals depend upon oxygen in the air. When oxygen declined, some organisms struggled to survive, while others disappeared from affected areas altogether. Certain portions of the seabed may have supported fewer scavengers than would normally be expected in healthier marine environments. This reduction in scavenging activity carried important consequences. When fewer animals disturbed carcasses, shells, and organic remains resting on the bottom, some materials remained intact for longer periods. Sediments accumulated around them, gradually sealing traces of life into the geological record. Under the right circumstances, this process improved preservation potential and increased the likelihood that evidence of ancient ecosystems would survive into the present. The mud itself also changed character when oxygen became scarce. Chemical reactions within sediment differ dramatically under low oxygen conditions. Organic matter decomposes along different pathways, minerals form in altered ways, and the appearance of deposited layers can shift noticeably. These processes contributed to the formation of dark, organic-rich sediments known as black shales, which occur in parts of the Cretaceous geological record. Such rocks preserve valuable information about ancient marine environments and the conditions that shape them. Viewed across broader stretches of geological time, these local patterns connect to larger events known as oceanic anoxic events. During portions of the Cretaceous period, substantial areas of the world's oceans experienced major oxygen depletion. These episodes affected marine ecosystems on a global scale and influenced the distribution of organisms, nutrient cycles, and sediment formation. The Western Interior Seaway formed part of this wider planetary story, recording evidence of environmental changes that extended far beyond North America. The contrast within the seaway could be striking. Near the sunlit surface, plankton supported food webs filled with fish, reptiles, birds, and countless smaller organisms. Energy flowed continuously through productive waters. Far below, portions of the seabed occasionally experienced oxygen stress, creating habitats governed by different biological and chemical rules. Two very different worlds occupied the same body of water, separated by depth rather than distance. This unusual balance between productivity and oxygen depletion did not emerge by accident. It developed within a climate system that shaped temperatures, circulation patterns, sea levels, and the movement of nutrients throughout the seaway, helping create one of the most distinctive marine environments of the late Cretaceous. The shape of the Western Interior Seaway was influenced by forces far larger than any animal that swam within it. Long before a mosasaur crossed its waters or a shark followed migrating prey through open channels, the planet itself had already prepared the conditions that allowed such a sea to exist. Climate formed the framework upon which the entire ecosystem developed. During the late Cretaceous, Earth was warmer than it is today. Temperatures varied across regions, as they always have, yet the overall climate belonged to what scientists describe as a greenhouse world. Carbon dioxide levels were generally higher than modern values, and the planet lacked the extensive polar ice sheets that characterize the present day. Ice still existed in some forms and locations, but the great permanent continental ice masses, familiar from recent geological history, had not yet become dominant features of the poles. With less water locked away as ice, sea levels remained elevated. Oceans spread across continental margins and flooded low-lying regions that would otherwise have remained dry land. The broad seaway extending through the center of North America emerged from this combination of geological and climatic circumstances. Water occupied space that today contains plains, farms, towns, and river valleys, creating marine habitats across enormous areas of the continent. Temperature influenced more than shoreline position. Ocean circulation also responded to greenhouse conditions. Water moves through the oceans because of differences in temperature, salinity, wind patterns, and basin geometry. When global climates change, those circulation systems adjust as well. Evidence from Cretaceous rocks suggests that some greenhouse intervals were associated with relatively warm, deep ocean conditions, a situation quite different from the cold, deep waters that characterize modern oceans. Warmth affected life throughout the marine system. In some regions, favorable temperatures and nutrient availability supported productive ecosystems. Plankton populations could flourish, providing energy for increasingly complex food webs. Small organisms fed larger ones, and those larger creatures became food for still bigger predators. Productive seas often supported impressive biological diversity, helping sustain the rich communities preserved in Western Interior Seaway fossils. At the same time, warmer conditions could create challenges. Increased productivity sometimes meant greater amounts of organic material sinking toward the seafloor. As that material decomposed, oxygen could be consumed from bottom waters. In certain settings, oxygen levels declined enough to stress organisms living near the sediment. Climate therefore influenced both abundance and limitation, helping generate environments where thriving surface ecosystems existed above areas experiencing periodic oxygen shortages. The relationship between heat, sea level, and marine expansion connected many aspects of the late Cretaceous world. Higher temperatures contributed to elevated sea levels. Elevated sea levels created extensive shallow seas. Those shallow seas opened ecological opportunities for marine reptiles, sharks, fish, birds, ammonites, turtles, and countless smaller organisms. Evolution responded to conditions that climate helped establish, filling available habitats with an extraordinary variety of life. Seen from this perspective, the Seaway was part of a larger planetary system. Climate prepared the stage, geography defined its boundaries, and evolution populated the waters with an ever changing cast of organisms. When that living world vanished, traces remained behind. Bones, teeth, shells, and sediments settled into the geological record, preserving evidence of bodies that would one day tell the story of this remarkable sea. A living ecosystem disappears the moment an organism dies. Muscles decay, colors fade, soft tissues break apart, and the movements that once connected predator and prey vanish from view. What remains is often incomplete, scattered, and altered by time. Paleontology exists because traces survive despite that loss, allowing fragments of vanished worlds to be assembled into meaningful stories. The process resembles an investigation built from evidence rather than observation. No scientist watched a mosasaur pursue prey through the Western Interior Seaway. No human witnessed a giant shark crossing those waters or a diving bird slipping beneath the surface. Knowledge comes from clues preserved in stone. Each fossil contributes a small piece of information, and those pieces gain value when examined together. Bones form part of that evidence. Teeth contribute another. Shells, stomach contents, bite marks, trackways, coprolites, and even the chemistry of surrounding rocks all carry information about ancient life. A fossil deposit can resemble a crime scene preserved across millions of years, though one governed by natural processes rather than human actions. The remains do not provide a complete account. They offer clues that must be interpreted carefully and tested against other clues. Among marine fossils, teeth often appear in remarkable abundance. Sharks help explain part of that pattern. Modern sharks continually replace teeth throughout their lives, shedding old ones and growing new replacements. Their Cretaceous relatives followed similar biological strategies. A single shark could leave behind large numbers of teeth without dying. Across thousands of generations, those discarded structures accumulated across seafloors and increased the chances that at least some would become fossilized. Marine reptiles also contributed durable teeth to the fossil record. Enamel resists decay and can survive conditions that destroy softer tissues. Bones, by comparison, face additional challenges. Currents may move them, scavengers can scatter them, sediment may bury some parts of a skeleton while leaving others exposed. As a result, paleontologists often encounter isolated elements rather than complete animals. Because evidence varies in strength, scientists distinguish between direct evidence and inference. This distinction forms one of the foundations of reliable paleontological interpretation. Direct evidence comes from observations preserved in the fossil record itself. A fish skeleton preserved inside the body cavity of a larger predator provides direct evidence of feeding. Tooth marks impressed into bone supply another example. Such discoveries record events that actually occurred. Inference works differently. An animal's anatomy may suggest how it hunted, moved, or interacted with its environment. Long jaws, powerful neck muscles, sharp teeth, streamlined bodies, and sensory adaptations all provide clues. Scientists can develop well-supported interpretations from these features, but the behavior itself is reconstructed rather than directly observed. The conclusion may be strong, yet it remains an interpretation built from evidence. Maintaining that distinction protects credibility. It prevents speculation from being presented as certainty and allows discoveries to be revised when new evidence appears. The goal is not merely to tell an interesting story. The goal is to build the most accurate reconstruction possible from the clues available. Some of the strongest clues preserved within the Western Interior Seaway come from the marks left behind when animals fed, traces that recorded moments of contact between hunter and prey long after the participants themselves disappeared. Some fossils preserve entire skeletons, others preserve only a tooth, a shell fragment, or a section of bone. Occasionally, however, a specimen captures evidence of contact between living animals. These discoveries are especially valuable because they record moments when members of the food web physically interacted. They transform ancient ecosystems from collections of species into communities connected through feeding, competition, injury, and survival. Among the most revealing examples are bones bearing bite marks. Mosasaur fossils from the Western Interior Seaway sometimes display damage that cannot be explained by normal growth or geological pressure. Grooves, punctures, and gouges appear on skeletal elements, preserving traces of encounters with large jaws. Some injuries healed during life, indicating that the animal survived long enough for bone repair to begin. Others show no signs of healing, suggesting that damage occurred near the end of life or even after death. Those marks do not automatically reveal the full circumstances surrounding an event. A bite could result from predation, competition, territorial conflict, scavenging, or feeding upon an already dead animal. Fossils rarely preserve enough information to distinguish every possibility. Even so, the presence of damage demonstrates that large predators regularly interacted in ways that sometimes left lasting physical consequences. Evidence from flying reptiles adds another layer to the picture. Certain pterosaur remains preserve indications of feeding interactions involving sharks. These discoveries show that boundaries between air and sea were more permeable than they may first appear. A carcass floating on the water, an injured animal struggling near the surface, or a feeding individual passing within reach of a predator could all create opportunities for contact. The fossil record preserves the interaction itself while leaving some details open to interpretation. Direct evidence becomes even stronger when prey remains are discovered inside predators. Earlier fossils from the seaway revealed fish preserved with meals still contained within the body cavity. Such specimens capture actual feeding events rather than inferred behavior. They provide snapshots of ecological relationships frozen at a specific moment in time. Few forms of evidence offer a clearer connection between predator and prey. To understand feeding traces properly, paleontologists examine details that might appear insignificant at first glance. The spacing between marks can suggest the arrangement of teeth in a jaw. Shape helps identify whether teeth were broad, narrow, serrated, or conical. Depth may indicate the force involved in the bite or the condition of the bone when contact occurred. Individual clues rarely stand alone. Meaning emerges when many observations are compared across multiple specimens. Interpretation always requires caution. Some damage occurs during active attacks. Other marks form when scavengers feed upon already dead animals. Currents, sediment pressure, and geological processes can sometimes alter bones after burial. Each possibility must be considered before conclusions are drawn. Scientific confidence grows when different lines of evidence point toward the same explanation. This careful accumulation of fragments reveals something important about the Western Interior Seaway. Its danger was never defined solely by the size of individual predators. The deeper story emerges from the extraordinary number of preserved interactions. Bite marks, broken bones, feeding traces, and last meals all document connections between species. Taken together, those fragments illuminate an increasingly detailed food web, one preserved piece by piece within the rocks of the vanished sea. At first glance, the Western Interior Seaway appears to be a story about giant hunters. Teeth, jaws, and towering predators dominate museum halls and fossil displays. A closer look reveals a different structure. Every large animal in that sea depended on countless smaller lives connected through an intricate network of feeding relationships. The most powerful predators occupied the upper reaches of a system supported by organisms so small they often escape notice entirely. Near the sunlit surface drifted microscopic producers, mainly algae and other planktonic organisms capable of converting sunlight into stored energy. These tiny forms of life floated with currents that crossed broad stretches of water. Though individually insignificant in size, their collective productivity formed the foundation of the ecosystem. They transformed light, nutrients, and carbon into living tissue, creating the first link in a chain that extended all the way to the largest marine reptiles. Small invertebrates gathered around this floating abundance. Minute crustaceans, larval animals, and other plankton feeding organisms consumed microscopic producers and converted that energy into forms available to larger consumers. Every movement through the water transferred energy upward. A cloud of drifting plankton could support thousands of feeding mouths, each becoming nourishment for something larger. Schools of small fish occupied the next layer. They moved through productive waters, harvesting plankton and tiny invertebrates. Their numbers mattered as much as their size. A predator could capture individual fish quickly, but entire populations served as living bridges connecting lower feeding levels to larger animals. Without them, energy would struggle to move efficiently through the ecosystem. Beyond these schools lived mid-sized fish and squid-like cephalopods. Cephalopods belong to the group that includes squid, octopuses, cuttlefish, and nautiluses. Fast swimmers and active hunters, they fed upon smaller prey while becoming prey themselves. Their position in the food web connected multiple pathways of energy flow. Fish consumed them, reptiles consumed them. Larger predatory fish pursued them through open water. Every successful hunt carried energy upward into another level of the system. At higher trophic levels, meaning feeding levels within an ecosystem, familiar giants entered the picture. Xiphactinus hunted substantial prey. Large sharks patrolled open waters. Plesiosaurs pursued animals suited to their particular feeding strategies. Mosasaurs occupied prominent predatory roles across many habitats. Their presence often dominates reconstructions of the seaway, yet none existed independently. A mosasaur required fish, reptiles, or other prey. Those prey animals depended on smaller consumers. Smaller consumers relied on plankton-rich waters sustained by microscopic producers. Death also contributed to the movement of energy. Scavengers recycled remains that settled through the water column or drifted across the seafloor. Fragments of carcasses fed animals that never participated in the original hunt. Nutrients returned to circulation, supporting new generations of organisms throughout the ecosystem. Even decay became part of the larger process. Viewed as a whole, the seaway resembles less a collection of separate creatures and more a living network. Every hunter depended on prey. Every prey species depended on resources below it. Every level rested upon drifting life suspended in sunlit water, The famous predators stood at the top of the structure, yet the foundation remained microscopic. When an entire system depends upon countless connections, one thought naturally follows. What happens when those connections begin to change? A glance across the Western Interior Seaway reveals an impressive collection of predators sharing the same body of water. Mosasaurs cruised through marine corridors, sharks crossed open expanses, large fish pursued schools of prey. Plesiosaurs occupied their own ecological roles. Their coexistence raises an important question about how so many hunters could thrive within the same ecosystem without eliminating one another's food supply. Part of the answer lies in niche partitioning, meaning species use different resources or hunt in different ways within the same environment. Even when several predators targeted similar categories of prey, they often approached those resources from different directions. Nature rarely distributes opportunity evenly. Small differences in anatomy, behavior, habitat preference, or hunting strategy can reduce direct competition and allow multiple species to survive side by side. Size created one layer of separation. A juvenile predator faced different opportunities and dangers than a fully grown adult. Large mosasaurs could pursue prey unavailable to smaller hunters. Mid-sized fish often targeted animals that would barely register as a meal for a giant reptile. Across the ecosystem, body size shaped which prey could be captured efficiently and which risks could be tolerated during a hunt. Water depth added another dimension. Some animals spent much of their lives in open water, far from shore. Others favored coastal environments, shallower regions, or particular layers within the water column. A predator feeding near the surface encountered different prey than one searching deeper zones. The same sea contained multiple habitats stacked upon one another, each offering its own challenges and opportunities. Speed also influenced success. Fast swimmers could chase agile prey through open water. Other predators relied less on pursuit and more on timing, maneuverability, or ambush. A streamlined body offered advantages in one situation, while a different build could perform better elsewhere. Every adaptation represented a compromise shaped by millions of years of evolutionary testing. Jaw shape further divided ecological roles. Sharks equipped with cutting teeth processed food differently from animals specialized for grasping slippery prey. Crushing dentitions opened access to armored organisms protected by hard shells. Long, narrow snouts interacted with prey in ways unlike broad, powerful skulls. Anatomy guided feeding possibilities long before a hunt even began. Prey choice completed the pattern. Fish, cephalopods, marine reptiles, shelled organisms, and other animals occupied different positions within the ecosystem. Predator diets often overlapped at the edges, yet complete overlap appears uncommon. Each hunter exploited opportunities best matched to its physical design and ecological circumstances. Such crowding created continual evolutionary pressure. Prey animals that detected danger earlier gained a better chance of survival. Faster escape responses could make the difference between life and death. Improved camouflage, schooling behavior, defensive structures, and sensory abilities all carried potential advantages. Every successful adaptation influenced the next generation. Predators faced pressures of their own. More efficient hunters obtained more energy, better movement, sharper senses, stronger jaws, and refined hunting behaviors improved feeding success. Young predators encountered an additional challenge. Before becoming dominant hunters, many had to avoid larger predators already occupying the upper levels of the food web. Across countless generations, These pressures accumulated into a continuing biological contest. Survival favored innovation, and innovation reshaped bodies. Teeth, skulls, limbs, tails, and sensory systems became records of that ongoing competition, revealing an evolutionary arms race written directly into anatomy itself. A fossil tooth often survives long after the rest of an animal has vanished. Muscle decays, skin disappears, internal organs leave little trace. Teeth, built from some of the hardest tissues in the vertebrate body, frequently remain behind as durable records of vanished lives. Across the Western Interior Seaway, countless teeth settled into sediments, carrying clues about how predators fed, competed, and survived. Each tooth shape reflects a particular solution to a recurring challenge. Food must be captured, controlled, processed, and swallowed. Different prey demand different tools. Evolution shaped those tools through countless generations, gradually refining structures that improved feeding success. In that sense, a tooth is more than anatomy. It is evidence of a long biological history written into mineralized tissue. Mosasaurs carried conical teeth designed for gripping and tearing. Their teeth were not built like scissors. Instead, they functioned as strong anchors, capable of securing struggling prey. Once a victim was caught, powerful jaws and body movements helped pull flesh apart or maneuver prey into position for swallowing. Looking at a mosasaur skull reveals a predator adapted for holding on to difficult quarry in an environment where escape opportunities were abundant. Nearby swam sharks equipped with a different strategy. Many predatory sharks possessed cutting teeth suited for slicing through flesh. Sharp edges transformed the mouth into an efficient tool for removing pieces of tissue. A bite could leave distinctive marks that sometimes remain preserved on fossil bones. Even without observing the animal directly, paleontologists can often recognize aspects of feeding behavior from the shape of the teeth alone. Tychodus followed another path entirely. Its pavement-like dentition formed broad, crushing surfaces capable of breaking hard prey. Shells that resisted piercing or slicing became accessible through force. The mouth functioned less like a trap and more like a crushing device. Such specialization opened ecological opportunities unavailable to predators focused on soft-bodied animals. Ziphichtinus displayed yet another design. Long, sharp teeth lined jaws built for seizing fish. Speed and timing mattered greatly in open water pursuits. Slender teeth helped secure slippery prey before it could dart away. Fossils preserving prey within the body cavity of Ziphichtinus provide direct evidence that this strategy succeeded, even if success occasionally carried its own risks. Hesperornis, one of the diving birds of the Late Cretaceous, also retained teeth. These structures likely assisted in holding fish captured underwater. Modern birds manage without teeth, yet Hesperornis occupied an earlier stage in avian evolution. Its dentition reflects a feeding style shaped by pursuit beneath the surface rather than pecking or tearing on land. Teeth alone never tell the whole story. Jaw leverage and skull structure matter as well. Broad attachment areas for muscles can indicate powerful bites. Skull shape influences how force moves through the head during feeding. Together, teeth and jaws form an integrated system whose design reveals how an animal interacted with its environment. For extinct predators, the mouth often provides the clearest glimpse into daily life. Hunting methods, prey preferences, and ecological roles frequently leave traces there. Every tooth represents a fossilized decision shaped by evolution, preserved across millions of years. Those decisions did not emerge in isolation. Geography, habitat, and the changing shape of the seaway continually influenced which adaptations succeeded and which disappeared. No shoreline remained fixed for long along the margins of the Western Interior Seaway. Water advanced across low-lying landscapes, then withdrew again as geological and climatic forces altered the balance between sea and land. Maps of the late Cretaceous often present the seaway as a stable feature, yet the reality was far more dynamic. Coastlines migrated across great distances, reshaping habitats and continuously altering the living geography experienced by the animals that inhabited this inland sea. As shorelines shifted, rivers carried fresh sediment from distant uplands into coastal waters. Sand, silt, clay, and dissolved nutrients entered the seaway through branching river systems that emptied into broad deltas. These deltas became productive environments where nutrients fueled biological activity. The meeting place between land and sea created conditions very different from those found far offshore. Water depth, sediment levels, salinity, and food availability could all vary considerably across relatively short distances. Coastal shallows supported ecological communities distinct from those occupying deeper central waters. Sunlight penetrated more easily through shallow environments, influencing productivity and shaping local food webs. Animals adapted to these regions encountered conditions unlike those present in the open seaway. Some species thrived near river mouths where nutrients were abundant. Others occupied offshore settings where deeper water and different prey opportunities dominated daily life. Changing shorelines influenced where animals could live, feed, and reproduce. A habitat suitable during one interval might disappear as water levels rose or fell. Marine organisms responded by shifting ranges, adapting to new conditions, or declining when environmental changes exceeded their limits. Geography acted as a continuing force shaping ecological opportunities throughout the seaway's history. Many species appear to have preferred nearshore environments. Coastal waters offered access to concentrated food resources and a variety of ecological niches. Other animals spent much of their lives in open water, moving through broader regions less tied to the changing contours of the shoreline. Large marine predators often traversed extensive areas, crossing habitats that smaller animals rarely occupied. These movements connected different parts of the ecosystem into a larger network spanning thousands of kilometers. Marine corridors also played an important role. The seaway linked distant regions, allowing animals to disperse across substantial portions of the continent. Movement through these corridors influenced evolutionary patterns and shaped the distribution of species across time. Connections between habitats could expand or contract as geography changed, affecting which populations interacted with one another. Fossils recovered from different parts of the seaway reveal that ecological communities were not identical everywhere. Certain regions preserve particular combinations of predators, prey, and environmental conditions. Elsewhere, a different collection of organisms appears in the rock record. These variations provide evidence that local geography influenced biological communities throughout the seaway. Scientists study these patterns through biogeography, the study of where life lives and why. By comparing fossil occurrences across regions, researchers can identify broad distribution trends and reconstruct how ecosystems were organized across changing landscapes. Studies of vertebrate distribution within the Western Interior Seaway have shown that geography, habitat preference, and environmental conditions all influenced where species occurred. The seaway was therefore more than a single body of water. It was a shifting mosaic of habitats connected by movement, separated by distance, and continually reshaped by geological change. As coastlines migrated and environments transformed, the conditions that supported this remarkable ecosystem gradually began to change as well. Maps drawn from the rocks reveal a gradual change unfolding across the heart of North America. The broad inland sea that had supported countless marine lives for millions of years was no longer expanding across the continent. Its boundaries shifted, its connections altered, and its waters slowly surrendered territory back to land. The transformation unfolded across immense stretches of time, measured not in generations but in geological chapters recorded layer by layer within stone. The Western Interior Seaway existed because several powerful forces happened to align. High global sea levels flooded low regions of the continent, while tectonic activity influenced the shape of the basin itself. Those conditions did not remain fixed. As the late Cretaceous progressed, movements within Earth's crust continued to reshape Western North America. Mountain building associated with tectonic activity altered drainage patterns and changed the geography surrounding the seaway. The continent itself was evolving beneath the water. At the same time, rivers carried enormous quantities of sediment into marine environments. Grain after grain, flood after flood, material accumulated across portions of the basin. Sediment that arrived from distant highlands gradually filled sections of the seaway floor. What had once been open water could become shallower through continued deposition. Shorelines adjusted in response, advancing into areas previously occupied by marine habitats. Sea level changes added another layer of complexity. Global sea levels rose and fell through the late Cretaceous, influenced by processes operating across the planet. When sea level declined, coastal regions expanded and marine waters retreated. Areas that had supported ocean life for long intervals could become isolated, transformed, or disappear entirely. The shape of the seaway became increasingly fragmented as these changes accumulated. Marine corridors that once connected distant regions narrowed as water coverage decreased. Pathways used by animals moving through the inland sea became more restricted. Populations that had previously shared connected habitats could find themselves separated by geography. Distribution patterns shifted as species responded to changing environmental conditions. Shrinking seas often place stress upon marine ecosystems for several reasons. Habitat area decreases, leaving fewer places for animals to feed, reproduce, and move. Ecological communities that once occupied broad regions become compressed into smaller spaces. Competition may increase when multiple species rely upon overlapping resources within reduced habitats. Environmental conditions can also become less stable. Changes in water circulation influence temperature, nutrient movement, and oxygen distribution. In some coastal settings, salinity may fluctuate as freshwater input and marine connections change. Prey species adjust their ranges in response to these shifting conditions, creating new patterns of abundance and scarcity throughout the food web. No single consequence applies equally to every organism. Some species adapt successfully to changing environments. Others shift their geographic ranges. Certain populations decline, while different forms expand into newly available ecological opportunities. The history recorded in the rocks reflects many responses unfolding simultaneously, not a single uniform outcome shared by every creature inhabiting the seaway. As waters withdrew and habitats became increasingly divided, the great inland sea entered a different phase of its existence. The ecosystem that had supported giant reptiles, birds, sharks, fish, and countless smaller organisms was already changing before its final chapter arrived. Beyond this gradual transformation, Another event still remained in Earth's future, one far larger than the retreat of the sea itself. A layer of rock found across much of the world marks a boundary unlike any other. Within that thin geological horizon lies evidence of a catastrophe that unfolded approximately 66 million years ago, closing the Cretaceous period and ending one of the most extraordinary chapters in Earth's history. The Western Interior Seaway had already been changing for millions of years, its waters withdrawing from parts of the continent, yet a far greater event was approaching from beyond the atmosphere. The trigger was the Chicxulub impact, named after the structure buried beneath the Yucatan Peninsula of modern Mexico. A large asteroid struck Earth with immense energy, excavating a crater more than 180 kilometers wide and releasing forces beyond ordinary geological processes. Shock waves spread through the planet. Wildfires ignited across many regions. Dust, soot, and vaporized material entered the atmosphere and altered environmental conditions on a global scale. Attention often focuses on the disappearance of non-avian dinosaurs, whose long dominance on land came to an end during this extinction event. The oceans, however, suffered losses just as profound. Marine ecosystems that had flourished through the late Cretaceous faced disruptions that reached from the surface waters to the largest predators. One of the greatest vulnerabilities lay near the foundation of marine food webs. Countless organisms depended directly or indirectly on microscopic plankton drifting through sunlit waters. When atmospheric debris reduced the amount of sunlight reaching Earth's surface, primary productivity declined. Photosynthetic plankton struggled under darker conditions. Cooling temperatures followed. Ocean chemistry changed. Evidence also suggests that acidification affected marine environments, adding further stress to ecosystems already facing severe disruption. As productivity weakened, consequences moved upward through feeding networks. Small consumers lost food sources. Predators, dependent on those consumers, encountered growing shortages. The intricate connections that had supported marine life for millions of years became increasingly unstable. Organisms occupying higher trophic levels remained tied to the productivity of the smallest drifting forms. Among the casualties were the ammonites, those coiled cephalopods whose shells had become familiar companions throughout the seaway's history. After surviving numerous environmental changes across vast spans of geological time, they disappeared during the end Cretaceous extinction. Their loss removed a major component of marine ecosystems and erased a lineage that had persisted for hundreds of millions of years. Marine reptiles also vanished from the world oceans. Mosasaurs, which had risen to become dominant predators in many marine habitats, disappeared entirely. Plesiosaurs, whose ancestry stretched far deeper into the Mesozoic era, likewise reached their end. Multiple marine reptile lineages that had shaped ocean ecosystems across millions of years vanished within this period of environmental upheaval. Life did not disappear completely. Several groups endured the crisis and continued into the world that followed. Sea turtles survived. Crocodilians persisted. Sharks remained part of marine ecosystems, as did many bony fish lineages. Birds, the surviving descendants of certain dinosaur groups, crossed the boundary as well and carried their lineage into the Cenozoic era. The rocks preserve this transition with unusual clarity. One world closes, another begins. Across the former seaway, fossils record the final presence of creatures that would never return, while survivors carried fragments of life's history into the uncertain aftermath that followed. The first chapters of recovery did not begin with giants. After the end Cretaceous extinction removed many of the dominant creatures that had defined marine ecosystems, the oceans entered a period of ecological rebuilding. Familiar waters remained, currents continued to move across the planet, and sunlight still reached the sea surface. Yet the living communities occupying those environments had been profoundly altered. Entire branches of life's history had vanished, leaving ecological space that would gradually be filled by survivors and their descendants. Among the groups that crossed this boundary were sharks. Their survival did not mean that nothing changed. Numerous shark lineages disappeared during the extinction event, and those that persisted entered a transformed world. Food webs had been disrupted, prey communities had shifted, and marine ecosystems were reorganizing. Through this transition, sharks demonstrated a resilience that had already carried their lineage through previous environmental crises. The forms inhabiting modern oceans represent only a portion of a much deeper evolutionary story stretching back hundreds of millions of years. Sea turtles also endured. The waters they entered after the extinction differed greatly from those occupied by their Cretaceous ancestors. Predator communities changed, coastlines evolved, marine ecosystems reorganized around surviving groups. Turtles adapted to these changing conditions and continued their long journey through geological time. Their presence in modern oceans serves as a living connection to worlds far older than humanity. Bony fish emerged from the extinction as another successful group. Many lineages survived and continued diversifying throughout the Cenozoic era. Freed from some former ecological constraints, fishes expanded into new opportunities and developed an extraordinary variety of forms. Coral reefs, coastal habitats, open oceans, and deep water environments all became stages for further evolutionary experimentation. Much of the diversity visible in marine fish today traces its roots to this long period of recovery and expansion. Birds survived as well, though only a portion of their broader dinosaur heritage crossed the extinction boundary. The lineage leading to modern birds persisted while all other non-avian dinosaurs disappeared. Those survivors carried forward anatomical and behavioral traits that would eventually produce the thousands of bird species alive today. Their continued existence transformed what might otherwise have been a complete ending into a story of continuity hidden within apparent loss. One striking absence remained in the oceans immediately after the impact. Marine mammals did not yet dominate marine ecosystems. Whales, dolphins, and other familiar marine mammals had not evolved when the asteroid struck Earth. Their story would begin later, when certain land mammals gradually returned to aquatic environments and underwent profound evolutionary transformations. The rulers of future oceans had not yet appeared. This contrast reveals how thoroughly the extinction reshaped life. The world of mosasaurs, plesiosaurs, ammonites, and countless other Cretaceous organisms came to an end. In its place, a different marine age slowly emerged. New ecological relationships formed. New dominant groups appeared. Familiar oceans hosted unfamiliar communities. Survival during this transition was rarely a matter of sheer size or strength. Flexibility often proved more valuable. Broad diets, adaptable habitats, effective reproduction, and the ability to exploit changing opportunities could make the difference between persistence and disappearance. Across millions of years, those survivors became the foundation from which a new ocean world was built, setting the stage for reflection on what the lost sea still teaches us today. The feeling begins with a map, not a map of strange continents or distant worlds, but a map of places that still exist today. Familiar names remain in their familiar locations. Rivers, plains, farms, highways, and towns occupy the landscape. Then the water appears. An immense inland sea spreads across the center of North America, covering regions now associated with grasslands and open horizons. The geography remains recognizable, yet everything important has changed. Kansas provides one of the clearest examples. Today, it is known for broad prairie landscapes and agricultural fields stretching toward distant horizons. During the Late Cretaceous, much of that same region lay beneath seawater. Fish swam where tractors would eventually travel. Sharks crossed routes that future roads would follow. Marine reptiles hunted through waters that no longer exist. The contrast feels unusual because the location itself has remained while its identity has changed completely. Across the Great Plains, layers of chalk preserve part of that transformation. These pale rocks seem ordinary when viewed from the surface, yet they originated within marine environments. Countless microscopic organisms lived, died, and settled through the water column. Their remains accumulated over immense spans of time, gradually forming thick deposits on the seafloor. What appears today as dry stone once began as drifting life, suspended within a living ocean. This perspective alters how familiar landscapes are understood. Ground that feels permanent becomes part of a much longer story. Hills, plains, and exposed rock layers reveal that Earth's surface is not fixed. Continents shift, seas advance and retreat. Ecosystems appear, flourish, and disappear. The world experienced by any one species represents only a brief chapter within a much larger narrative. Fossils strengthen this connection between present and past. A shark tooth recovered from a field is more than an isolated object. It links an ordinary landscape to an ecosystem filled with predators, prey, currents, migrations, births, and deaths. The distance between those worlds collapses. A person standing in a modern pasture may be separated from a Cretaceous ocean by millions of years, yet the evidence remains directly beneath their feet. Part of the emotional weight comes from scale. Human history occupies a relatively narrow slice of time. Cities, nations, and civilizations rise and fall within intervals that appear brief when compared with geological change. The Western Interior Seaway existed for millions of years. Entire evolutionary stories unfolded within its waters. Then the sea vanished, leaving traces scattered across regions that no longer resemble their former selves. A field may appear calm and familiar, yet its rocks can preserve records of giant fish, marine reptiles, diving birds, drifting ammonites, and sharks moving through an inland ocean. Those discoveries remind us that landscapes carry memories, extending far beyond human experience. The surface we recognize today represents only the latest version of a place that has worn many different forms. The Western Interior Seaway remains unsettling because it reveals how thoroughly Earth can reinvent itself. Oceans become plains, seafloors become grasslands, living communities disappear and are replaced by entirely different worlds. Stability exists, but mostly within the span of a human lifetime. Across deeper stretches of time, change is one of the most persistent features the planet has ever known. A shoreline appears, water spreads across a continent, and life begins to respond. No blueprint directs the process. No final destination waits at the end. Organisms encounter new opportunities. Some succeed, others fail, and entire ecosystems emerge from countless interactions unfolding across immense spans of time. The Western Interior Seaway offers one of the clearest examples of this process written into the geological record. When warm, shallow seas flooded the center of North America, they created habitats that had not existed there before. Sunlit waters supported microscopic producers. Small animals fed upon them. Predators followed. Ecological relationships multiplied. Each living thing occupied a position shaped by food, competition, reproduction, movement, and environmental conditions. From these interactions, a complete marine world assembled itself piece by piece. The process did not stop once the ecosystem became established. Evolution continued working through every generation. Marine reptiles that had entered the oceans long before the late Cretaceous carried ancestral traits inherited from land-dwelling predecessors. Given millions of years within aquatic environments, some lineages acquired bodies increasingly suited to life in the sea. Limbs transformed into flippers, tails became propulsion systems. New hunting strategies emerged. Eventually, giant marine predators appeared, occupying ecological roles unavailable to their distant ancestors. Fish followed similar patterns. Productive waters supplied abundant prey, supporting larger and more specialized predators. Certain species grew to extraordinary sizes, becoming dominant hunters within portions of the ecosystem. Their success reflected opportunities provided by food availability, environmental conditions, and evolutionary adaptation operating together across long intervals of time. Birds reveal another dimension of the same story. Early avian lineages experimented with different ways of living. Some remained associated with flight and aerial feeding. Others entered marine habitats more deeply. Hesperornis and its relatives became specialized diving birds adapted for underwater pursuit. In those lineages, wings lost much of their former importance while swimming abilities increased. Evolution reshaped existing structures to meet new ecological demands. Viewed together, these examples reveal a broader pattern. Evolution possesses no final form toward which life steadily advances. There is no permanent champion and no ultimate design. Organisms persist only as long as their adaptations remain effective within changing environments. Success creates opportunity, yet environmental change can alter the conditions that once favored that success. The Western Interior Seaway illustrates this principle repeatedly. Species appeared, diversified, interacted, and disappeared. Entire groups flourished for millions of years before vanishing. New forms emerged to occupy available ecological space. Extinction and innovation existed side by side, each influencing the future possibilities available to life. For that reason, the deadliest ocean was never defined solely by danger. It was also a place of extraordinary productivity. Nutrients moved through complex food webs. Predators competed for resources. Prey adapted to survive. Ecological pressures generated biological diversity on a remarkable scale. Every tooth, shell, fin, flipper, and feather reflected countless generations shaped by survival within a changing world. The Western Interior Seaway serves as a mirror because it reveals evolution in motion, building ecosystems, reshaping bodies, and replacing old communities with new ones. By following its story from beginning to end, a deeper understanding emerges of what this lost ocean truly represents and what its history still teaches today. Looking back across this vanished seaway, the title begins to carry a broader meaning. The deadliest ocean was never defined by size alone. It was not created solely by giant predators, enormous jaws, or dramatic encounters. Its character emerged from an entire living system, one built from abundance as much as danger, from opportunity as much as competition, and from countless relationships connecting every level of life. A continent stood divided by water. Shorelines stretched across regions that today seem inseparable from dry land. What is now farmland, prairie, and rolling countryside once formed part of a marine realm extending across the heart of North America. The transformation feels difficult to imagine because the landscape, familiar to us, belongs to a different chapter of Earth's story. Within those waters, mosasaurs occupied positions near the top of complex food webs. Their presence reflected millions of years of evolutionary change, turning descendants of land reptiles into powerful marine hunters. Open water also carried sharks, each lineage shaped by different feeding strategies and ecological roles. Some sliced through flesh, some crushed armored prey, and others occupied niches that reduced direct competition. Together, they formed part of a crowded predator community unlike anything found in modern oceans. Large fish added another dimension to that world. Xiphactinus remains one of the clearest reminders that danger could come from unexpected directions. Fossils preserving prey within predator reveal moments frozen across immense spans of time. They show ecosystems operating through interactions that once lasted only seconds but remained recorded for tens of millions of years. Above the surface, flight offered no complete separation from marine life. Pterosaurs traveled over the seaway while feeding opportunities drew them toward the water. Early birds entered marine habitats in different ways, some becoming skilled divers that pursued prey beneath the surface. Air, water, and seafloor connected into a single ecological network where boundaries remained permeable and constantly crossed. Far below the waves, oxygen-poor mud accumulated layer after layer. In some settings, those sediments preserved traces that active ecosystems would otherwise erase. Bones settled there, shells remained. Teeth survived. Chemical signatures endured. The seafloor became a record keeper, storing fragments of vanished lives long after the organisms themselves disappeared. What the living ocean forgot, the sediment sometimes retained. Seen together, these pieces reveal why this seaway occupies such a distinctive place in Earth's history. Productivity fueled growth, competition shaped adaptation, predators influenced prey, environmental change altered opportunities. Evolution assembled communities, transformed them, and eventually replaced them. No species stood apart from the larger system supporting it. Perhaps the deepest lesson comes from recognizing how many different worlds Earth has hosted. The planet does not possess a single, unchanging history. It has carried forests unlike any alive today, skies filled with unfamiliar creatures, and oceans governed by ecosystems that no longer exist. The sea explored throughout this journey was one of those worlds. The ocean we know is only one version. The Western Interior Seaway was another. Let me know in the comments which creature, fossil, or discovery stayed with you most. And if you enjoy calm journeys through Earth's deep past, ancient oceans, and the strange science of lost worlds, consider subscribing for more explorations still waiting in the stone record.